The next unit is Electronics and Semiconductor, which is your unit 8. So here we will learn about semiconductors, the types of semiconductors, about diodes, triodes, and how they are used as rectifier, as amplifier, etc. Okay, so let us first start with what is a semiconductor. Semiconductors ki hoy bahute jana already. Semiconductors are those materials whose electrical conductivity lies in between that of conductors and insulators. Okay, so here you can see the band energy diagram of a semiconductor at absolute zero. So what happens is, here you can see this one is the valence band. A band to koa hoy valence band. This band is known as conduction band, and the energy difference between these two bands is known as the forbidden gap or energy gap. Okay, band gap buliu koa hoy. So the band gap in case of semiconductor is starts from 0.2 electron volt to 2.5 electron volt. Mane 3 electron volt ke hoday band gap to kom hoy in case of semiconductors. So here you can see the valence band is completely filled with electrons and the conduction band is completely empty. So this case is only at absolute zero. Jetia temperature to absolute zero consider kora hoy, tetia conduction valence band to completely filled hoy thake with electrons aru conduction band to empty hoy thake. But as the temperature rises, suppose it is kept, this semiconductor is placed at room temperature, what happens? Some of the electrons in the valence band will gain energy to they will be able to jump into the conduction band, and those electrons will act as free electrons, and those electrons will be responsible for conduction of electricity. So as the temperature increases, the conductivity of a semiconductor will increase. Okay, so this diagram is only at absolute zero. So in room temperature, what will happen? You can draw as valence band of electrons disa, conduction band of ketaman electron thakibo, baki rest of the thing will be the same. So next is the types of semiconductors. So there are mainly two types of semiconductors. Number one is the intrinsic or pure semiconductor. Number two is the extrinsic or impure semiconductor. Pure mane jibu natural hoy, ami eko add nokoru. Impure mane obviously we are adding something, adding some kind of impurity. So that is why they are known as impure semiconductors. Impure semiconductors are again divided into two types, N-type semiconductor and P-type semiconductor. So first of all, let us see what is an intrinsic semiconductors. So these semiconductors, what happens, you can see here an example. I have taken the example of silicon, germanium. Natural pure germanium is also an example of intrinsic semiconductors. So at suppose 0 degree Kelvin, what happens here? The valence band is completely filled, and the thermal energy of those electrons, here you can see the electrons, and the electrons are forming a what? A valence band between the atoms of the silicon. Okay, so therefore at 0 degree Kelvin, what happens? A pure semiconductor, this pure semiconductor is behaving like an insulator. Yet eko conduction hua nai, because they are at 0 degree Kelvin. But when the semiconductor is kept at room temperature, then some of the valence band electrons will gain sufficient energy so that it can jump into the conduction band, and they will become what? Free electrons. And those free electrons, when they will, suppose here there is, you can see one, this one is a valence electron. Okay, 0 degree Kelvin he bone to bhitor humai asile, but when the temperature will increase, these valence electrons will gain energy and they can jump to the conduction band. Conduction band of jodi electron to gusi jay, yat ki thaki jabo, here it will leave behind what is known as a hole. So the next type of semiconductor is extrinsic or impure semiconductors. So what happened? Here you have to learn what is doping and what is a dopant. So if I add some kind of impurity atoms in small amount to a semiconductor, then that process is known as doping. So doping ki process hoy jitu moi additionally at the impure atom kisuman small amount of the semiconductor logot add kori dim. Okay, so that process is called doping, and the added impurity is called dopant. Jitu moi impurity add korim, he impurity to ki koa hoy? Dopant buli koa hoy. And that semiconductor which contains the impurity atoms, that is known as a doped semiconductor or an impure semiconductor or an extrinsic semiconductor. So depending on what I have added, depending on what is the impurity, moi ki kind of impurity add korisu, hetuk loi extrinsic ba impure semiconductor eta duta type thake. Number one is N-type semiconductor, number two is P-type. So first of all, let us see what is an N-type semiconductor. So suppose I have taken a pure elemental silicon, or you can take germanium. So silicon semiconductor me eta loisu, then I have added a small amount of impurity of some kind of element which has 5 valence electrons, like suppose arsenic, phosphorus or antimony. Here you can see I have added one antimony. Sb is antimony. Okay, so what happens here? There will be one free electron which will be left. Valence band board thakibo duta electron aru yate the extra electron da roi jabo which is the free electron. So this free electron will be available as a current carrier. Hey, free electron will be responsible for the carrying of current. So that will be responsible for the conductivity of the semiconductor. And each impurity atom I add will donate one free electron to the semiconductor. Depending moi kimanta atom add korisu, impurity atom add korisu, himanta moi jimane besi impurity atom add korim, himanta free electron besi pabo semiconductor to. So such impurity elements are known as donors. Okay, donors kyo kwa hoy because yoti donate kori ase eta free electron for the conductivity of the semiconductor. So the semiconductor which contains the donor type impurity is known as the N type semiconductor, because here the current carriers are produced because of one negative charge, because free electron keta current di ase and you know that electrons carries negative charge, so those are known as N-type semiconductors. N mane ki denote korise negative. Okay, the free electrons which are produced are called the excess electrons, and the electrons here are the majority carriers and the holes are the minority carriers. And here in the right side, the diagram you are seeing is the energy band diagram. Here we are denoting the valence band, jitu tumalke jana, band gap jana agor diagram dekhaisu, conduction band aru jitu eta dashed eta band dekhisa hetu hol donor level, mane jibur impurity elements ami add korilu, donors add korilu, hihotor eta nijor energy level ase which will be close to the conduction band, because obviously they are conducting, so it will be close to the conduction band. And this one is the energy band diagram for N-type semiconductors. So in case of N-type semiconductors, what we did is we added pentavalent impurities, pentavalent atoms to a semiconductor. So ami ki korisilo enikwa kisuman elements jar number of electrons in their valence band or the valence electrons number is 5. So those we added to the semiconductors to get N-type semiconductors. So suppose in place of pentavalent impurity jagat jodi moi trivalent impurity add koru. Trivalent impurity is those elements or atoms which have 3 trivalent mane tinta valence electrons jar ase. Suppose for example you can see indium or gallium ami jodi add koru tetia semiconductor jitu semiconductor ami pam, those semiconductors are known as p type semiconductors. So what happens here is that when you add a trivalent impurity, then what happens is only 3 of the covalent bonds will be filled and there will be a vacancy in the fourth bond. The fourth bond will not be formed because it will constitute a hole. At a hole rose up. This one is a hole, you can see here. Tinta band fill up holes up, but because it is a trivalent impurity, fourth number electron to turn 9. So this covalent bond will not be formed and one electron will be there. The other electron, the place of the other electron will be taken by a hole. So these impurities are known as acceptors. Ebur impurities, agor impurities burok ami ki boli koisilu, donors boli koisilu. And here in case of p type semiconductors, the impurities are known as acceptors. Why? Because these impurities, they make available positive carriers because they create holes which can accept electrons. Sihote amak ki di ase, trivalent impurity amak holes di ase aru ei hole burot ami electrons bur ahi accept koibo pare, ei hole bure accept koibo pare electrons, so they can accept, so those are known as acceptors. Okay, so this unfilled energy level is located in the near the valence band. Last case ot ki hoisile donor level to korisile conduction band or usor asile. So here those acceptors, you can see in the right hand side, the acceptor level is near the valence band. So those impurities which are known as acceptor, they have a energy level, these are the energy level ase aru hetu near the valence band with the dashed line, that is called the acceptor level. So the impurity atoms which causes generation of holes inside the semiconductors, they are known as acceptors, and the semiconductors which have acceptor type of impurity, those are known as p type semiconductors. And here the current carriers are positive charges holes. N-type semiconductors ot ki asile current carriers were electrons which are negatively charged, so hekarne hiotok N-type boli koha hoisile because N mane negative. But here in case of p-type, what happens, the current carriers are the positive carriers, positive charge hole, so hole p positive, so they are known as p-type semiconductors. So the next topic we will learn is thermionic emission, and then we will learn about vacuum tubes and the types of vacuum tubes. So you know that there are some loosely bound electrons in metals and semiconductors who have sufficient energy to move away from the atom and move in any random directions, and those electrons are known as free electrons, which are responsible for the current conduction in case of metals or conductors or semiconductors. So what happens at ordinary temperature, that is at room temperature, these free electrons, they cannot escape from the metal surface. To enable them to escape from the metal surface, we need to provide some additional amount of energy which is equal or greater than the work function of that specific metal or semiconductor. So what is work function? Agor video saba work function ma pohaisu in photoelectric effect. So then you will know what is work function, and then also you will know that work function ke always ami jitu energy provide kuru hoda work function ke besi hobo laibo or equal to hobo laibo, so that we can make an electron escape from its metal surface. Okay, so this extra energy which we need to provide, it can be provided by raising the temperature in the metal. So temperature jetia ami increase kuru, temperature mane temperature pa thermal word to temperature pa ahise. So this process of emission of electrons from the surface of any conductor by providing by raising the temperature of that conductor is known as thermionic emission. মানে আমি টেম্পারেচাৰ ৰাইজ কৰি এক্সটাৰ্নেলি ইলেক্ট্ৰনছবিলাক ইমিশ্যনত আমি হেল্প কৰিছোঁ, তো চ' ডেট প্ৰচেছ ইজ কল্ড থাৰ্মাইনিক ইমিশ্যন, and the flow of these electrons or the thermions which gives rise to a current, that current is known as thermionic current. So based on this thermionic emission principle, there are some electronic devices, simple devices, which are known as vacuum tubes. So vacuum tubes bilak simple electronic device hoy which runs in the principle of thermionic emission. Okay, so the basic, when you are asked what is the basic work principle of a vacuum tube, you will write thermionic emission. So what happens, vacuum tubes is a glass tube with which has its gas removed, obviously because it has to create a vacuum. Bhitorat tar he glass tube to bhitorat gas na thake, vacuum thake, and vacuum tube contains electrodes which can control the electron flow, and these vacuum tubes are used in early computers as a switch or as an amplifier. So depending on the number of jenenge ma kolu electrodes thake vacuum tubes er bhitorat, and depending on the what number of electrodes are present in a vacuum tubes, there are different types of vacuum tubes. Suppose if there are 2 electrodes in a vacuum tube, then that vacuum tube is known as a diode, and if there are 3 electrodes, then that vacuum tube is called a triode, and if there are 4 electrodes, then it is known as a tetrode, and pentode, and then hexode, and so on. Okay, so here basically we will learn what is a diode and a triode. So first of all, see the diagram of a diode, a vacuum tube diode. It consists of an anode and a cathode. Yet dekhisa, this one is the anode and this one is the cathode, and the anode is also known as the plate bulio koa hoy. So what happens here, the figure you can see, when the cathode is heated, it gives off electrons via the principle of thermionic emission. The cathode ami heat provide kuru and it will give off electrons, and then by applying a positive voltage to the anode ami positive voltage eta provide korisu, these electrons which are emitted by the cathode are attracted to the plate, and hence there is a current created. Because ami anode positive voltage eta provide korisu, here you can see that electrons are negatively charged, positive and negative or attract koribo, and the anode can attract those electrons towards itself. Okay, and hence a current is created which is known as a thermionic current. So these diodes are commonly used for rectification. And what is rectification? Rectification is the conversion of AC to DC, or alternating current to direct current. Next, you can see a vacuum tube triode. Next diagram to saw, that is a vacuum tube triode. So the triode has an extra electrode, anode thake, cathode eta thake, and there is a third electrode which is called the control grid. The third electrode, it enables the vacuum tube to be used not just as a rectifier but also as an amplifier of electrical signals. I mean, compaisu je diode to kiho kan use kora hoy, rectification at use kora hoy as a rectifier. But in vacuum tube triode, because of the presence of the control grid, the third number of electrode, it makes possible for the triode to be used as a rectifier but also as an amplifier. So rectification and amplification dutate triode use kora hoy. And this control grid, it is placed between the cathode and anode, and by adjusting, what does the control grid do? By adjusting the voltage applied to the control grid, we can control the number of electrons which flows from cathode to anode. Cathode anode position eki hoy ইয়াৰ নিচিনা just third electrode eta ase which is called the control grid. namot gom paisa control grid mane ki kiba ta control koribo pare. So by varying the voltage, jiman khini voltage amak kom beshi lage ami apply kori ami ki koribo paru, kiman khini electron cathode pa anode leke flow hobo hetu ami control koribo paru with the help of the third electrode. So the next thing we are going to learn is a p-n junction diode. So if I take a germanium or a silicon crystal and I dope it in such a way during the manufacturing process that half of it is p-type and the other half is n-type, then the thing which is formed is known as a p-n junction diode. Okay, you can see in the figure here. ইয়াত মই এটা semiconductor লৈছো, তাৰ আধাটো মই এনেকে ডোপিং কৰিছো যাতে হেতু এটা p type semiconductor হয়, and the rest half is a n type semiconductor, then that is called the p-n junction diode. ইয়াত দুটা ফিগাৰ আছে. The first one shows the unbiased p-n junction. Unbiased মানে any kind of external voltage আমি provide কৰা নাই, that is unbiased. And তলত যি দুটা আছে, that is a biased p-n junction. Biased মানে আমি externally voltage apply কৰিছো. So you have to know the difference in the phenomena of unbiased p-n junction and when you give external voltage to the p-n junction. So what happens? First we will see the unbiased p-n junction. That ki hoise. So as you know that in the p-type semiconductors, holes are the majority carriers, and in n-type semiconductors, electrons are the majority carriers. So what will happen, because the p region has a majority of holes and then the n region, so the holes will try to go from the higher density to the lower density. Mane hole bor move koribole lobo from p to n region. And similarly, the electrons, which are the majority carriers here, they will try to come from the n towards the p region, because density electron yat besi ase yat kom ase, so they will try to move from the higher density towards the lower density. And because of this diffusion of the free electrons from the n to the p region and of the holes from the p to the n region, these holes and electrons, they will recombine near the junction, and the region around the junction, it does not contain either free electrons or holes, and this region is therefore known as the depletion region, because depletion word to I say from depleted mane it does not contain that region, that small region in the middle does not contain any kind of charged electrons or positively charged holes, and there is also a potential drop that is developed across this junction, and that is also known as barrier potential, and that potential prohibits the further diffusion and recombination of holes and electrons. So coming towards the biased p-n junction diode, here you can see two diagrams. Number one is forward biased, number two is reverse biased. So if I connect a battery to the p-n junction in such a way that the positive terminal of the battery is connected to the p-type region and the negative terminal of the battery is connected to the n-type region, then the p-n junction is said to be forward biased. Okay, and the reverse one is tar opposite to ki hobo. If I connect the p-n junction diode in such a way that the positive terminal of the battery is connected to the n region and the negative side is connected to the p-type region, then the p-n junction is said to be reverse biased. The figure you're seeing here is a forward biased p-n junction. Here you can see I have connected the p side or the p region to the positive terminal of the battery, and the n region is connected to the negative terminal of the battery. And because of this condition, what happens? The holes in the p region, they will move towards the n region passing through the junction. Because why? Here there is a negative terminal. Negative terminal will, the positive holes will be attracted towards the negative terminal of the battery, so they will try to move this side. A bostudu a holes bur jiman ase hiati efale jabole sabo. And similarly, on the other hand, what happens? This one is the positive terminal of the battery. Electrons are negatively charged. Electrons will be attracted towards this side of the battery, so electrons will try to come to this side. Tete ki hobo? P side to jodi efale jabole sai, n side to efale ahibole sai, then with this the depletion layer will what? become narrower, depletion region to kumi ahibo. So in case of forward biased PN junction, the depletion region is always decreased. Remember this, in case of forward biased PN junction, the depletion layer reduces. So the next is a reverse biased PN junction diode. So here it will just be the opposite case of the forward biased condition. So here you can see the P region is connected to the negative terminal of the battery and N region is connected to positive terminal of the battery. And because of this bias condition, what happens here, the holes will be repelled by last case of ki holes bo positively charged hoy, yet negative terminal asile, so they were getting attracted. Now here there is positive terminal of the battery and holes are positively charged, so they will not be attracted, rather they will be repelled. Okay, and similarly electrons bo yale ahibo na sabo, electrons bo yar par repel hobo, so electrons will try to move there. So holes bo ifale ahibole saise, electrons bo ifale sabole saise, and in that situation what will happen, this depletion region will increase. Ebar depletion region to increase over. So in case of reverse biased PN junction diode, the depletion layer increases. Diodes can be used as a rectifier and also as an amplifier. In case of rectification, diodes can be used as a half-wave rectifier and also as a full-wave rectifier. So rectification is the process of conversion of alternating voltage or current into direct voltage or current. Mane in simple terms kobo para rectification mane ami AC pora DC le jodi convert kori asu, convert kobo paisu he process to koa hoy rectification. So because the diodes have the ability to respond only when the plate or the anode is at a positive potential with respect to the cathode, diodes bure tetia he current conduct kore jetia the anode is at a positive potential with respect to the cathode, and when there are cases when the anode is at a negative potential with respect to the cathode, then there will be no current conduction through the diode. Okay, so now let us see how what is a half-wave rectifier. So here you can see the circuit diagram for a half-wave rectifier. There is an alternating voltage source which is connected to the primary coil of a transformer. This one is the primary coil of a transformer. This one is the alternating current or voltage to hold into time, into voltage, input voltage, into hold AC voltage. Okay. So what happens here, in the circuit, the voltage is supplied by the source across the secondary, and that is the input voltage written as VIN, and there is a load resistance RL which is placed in with series to the diode. A RL to the dikhisa, it will load resistance that is placed in series to the diode, and we know that for an AC supply it has a two cycles. It has two cycles. One is a positive half cycle and another one is a negative half cycle. AC current to enake jay eta positive thake 0 para maximum ke jay ako 0 le nami ahe, and the same is repeated in the negative half, 0 para minus of negative maximum value to leke touch kori ako hi 0 leke khuri ahe. So one is positive half cycle, the next one is the negative, positive negative, positive negative enake AC2 current to flow hoy. So when the positive half cycle is applied to the plate, when the first positive half cycle to jetia apply kora hoy plate, then it is at the positive potential with respect to the cathode, and therefore the plate current is obtained in accordance with the variation of the positive half cycle. Mane 0 para maximum to 0 teneke ami current to pam, because why, because the positive half cycle jetia soli thake, then the plate is at a positive potential with respect to the cathode, therefore the current will flow through the diode to dikhisa etu P, etu N. This is the diode which is connected across the in the circuit. Okay, so ami positive cycle jetia sole mane output or ami teneke positive cycle to pump. But what happens in case of the negative half cycle, the current is flowing across RL, but during the next half cycle, in that is the negative cycle, there will be no plate current, because the anode or the plate will be at the negative potential with respect to the cathode, so there will be no current flowing through the PN junction diode. So ami output of ki pam, ei juntu current ase, AC voltage to juntu ase, hetu ami output of napam, hetu rectify ho jabo, hetu cut khai jabo. Why? Because this the anode was at a negative potential, ei juntu negativity ase, hetu karone cathode comparison tar negative hua karone PN junction diode 3D hi cycle to half cycle to pass হৈ নাযাব. So every positive cycle will pass through the PN junction diode and the negative cycle will be cut off from the output voltage. So output voltage to kind of ami eniko pam. We will get every positive cycle and negative cycle kida ami napao. So this one is known as the half wave rectifier because yat ami adha cycle to kati pelua hoise and output ot ami eta DC voltage paisu. So the next one is the full wave rectifier. So in a full wave rectifier, the circuit has two diodes now. Each diode is for one half cycle. One half cycle. Mane duta diode thake edu circuit D1 and D2. D1 is for the positive half cycle rectify koribo. D2 is for the negative half cycle of the AC input, and there is a multiple winding transformer which is used whose secondary winding is split equally into two halves and there is a common center tapped connection which is known as C. This one is the center tapped connection. This one is the midpoint of A and B and it is in the winding of the transformer. RL here is the load resistor. Load resistor to agora mi yad disilu, but here it is given so that D1 and D2 dutar karone common ke eta load resistor diya hoise, and this configuration it will result in each diode conducting in turn when its anode terminal is positive with respect to the point C. Okay, so what happens when point A of the transformer is positive with respect to the point C, that is in the positive half cycle of ki hoy, point A is at a positive potential with respect to point C, then the diode D1 will conduct in the forward direction. Mane forward bias condition at he current to conduct koribo in this direction, and the positive half cycle will be got in the output voltage of ami he positive half cycle to pump. And in the next case, in the negative half cycle of ki hobo, the point B will be at a positive potential with respect to point C, and then here in the first case D1 was used, in this case D2 will be used. This D2 will conduct in the forward direction and the current will flow in this direction. Okay, so this negative cycle we will get it here and so on. Because দুটাতে আমি forward direction পাইছো, so both every positive cycle will also be in the positive side, negative cycle to ami positive side ote pam because yat forward bias condition of current to flow hoy ase. The next topic is light emitting diode or LED. LED jitu ami commonly use kori thaku, the small lights. So these small lights are heavily doped forward biased PN junction. Yet dekhisa, this one is the N region, this one is the P region. They are doped such that the first layer is N, second layer is P, and this heavily doped PN junction diode what they does, they converts the electrical energy into optical energy, or optical energy to infrared region hole visible light or region of thake, so that the light is visible. Okay, and this one is the symbol of LED. It is just like the normal PN junction diode, just arrow tinta di dia hoise to represent the optical energy that is being released by the light emitting diode. So when this diode is forward biased, then you know that electrons and holes are moving fast across the junction or across or here they move koi thake from, like for example electrons bur N to P leke ahe, holes bur P pa N leke jai, so they are moving fast across the junction and they are combined constantly. So they are removing out one another itwe anto cancel out kori ase and they are combining constantly, and soon after the electrons are moving from the N type to the P type, then it combines with the holes and it disappears. So what happens is they are gaining stability and it gives a little burst of energy in the form of a tiny packet of photon or light. So basically they are converting the electrical energy which is trapped inside them into optical energy, and those are known as LEDs. You already know the uses of LEDs. They are used in optical communication, they are used in alarm systems, they are used as indicator lamps, they are used in domestic purpose like bulbs and electric tubes, etc.